All right, today we're going to look at Bernoulli's principle. So the first thing is talking about how flow works for different fluids. So again, we are going to assume that these are ideal fluids, which means they can't be compressed, means they don't have viscosity, and they're going to flow smoothly through the pipe. They're not going to spin. It's going to have kind of a straight flow all the way across. Now, the volume that fluid is flowing past is called the volumetric flow rate. We use a Q for the volumetric flow rate, which is really just a placeholder for a type of rate. So Q is equal to, and to find that, it's the speed that liquid, that our fluid is moving through a given area. So to kind of write that out, all we have to do is multiply the area of the pipe times how much material is actually going through it, which is the flow velocity. So we have Q again, which is the volumetric flow rate. And this is going to be volume per time. So units would be meters cubed per second. Then we have A, which is going to be the cross-sectional area of our pipe or whatever our tube is that it's flowing through. If you remember cross-sections from geometry, it's when you take a shape and you kind of like cut a slice out of it, and you were to take that shape. So typically, something like this, if you were to make a slice right here through the pipe, that you would see a circle. The area of that circle is our cross-sectional area. And then we have V, which was essentially the volume or the speed of our liquid. So flow velocity. So unit-wise, we have meters per second for velocity, and then cross-sectional area would be meters squared. Which makes sense if you think of the units, because when you multiply this across, we would have meters cubed on the top divided by seconds, which is the same thing we get over here for volume per time, which is the volumetric flow rate. So what they look at in doing this is two different places. So you have like location 1 and you have location 2. And you're saying, based off of this information, what is the rate of flow acting at that point? Now, the volume of water must be equal to the volume leaving. So the amount of volume that comes in has to be the same as the volume coming out. So in order for that rate to be exactly the same, if the tube is smaller, like on this end, it has to come out a whole lot faster because, again, the same amount of volume has to be entering and leaving at the same time. And so because of that, we know that the volumetric flow rate, Q, has to be exactly the same. I guess we have plenty of room here. And so then we know that the volumetric flow rate for any place on our pipe, so we'll do like area 1, times the flow rate at that location, has to be equal to the same thing in a different location. The area at that location times the speed at that location. This right here is called the principle of continuity, which just says that the flow rate has to be equal for all points within an isolated stream. So as long as there's nothing else that's going to change the amount of liquid in this pipe or in this location, then this has to be true. So if the pipe narrows, the flow must, and when I'm saying flow, I'm talking about the speed here. So as the pipe narrows, that means that the cross section is going to decrease. Since Q has to stay the same, that means that the velocity must increase to kind of account for that. So the flow must increase in speed. It must be traveling faster through the outside. You can kind of think of this like as a garden hose. that if you take the end of the hose and you pinch one end of it, you are decreasing the area and the speed goes way faster out of the pipe. So you can actually get it to go through the hose a lot, out one end a lot faster, so it shoots further. All right, so we have an example here. Water is flowing from the wider section of the pipe that has an area of 0.08 meters squared. So we'll say the area 1 over here is 0.08 meters squared. Into a narrower section of the pipe, so area 2, which has an area of 0.05 meters squared. The water is moving with a speed of 18 in the narrow section, so the velocity at this location is 18 meters per second. We want to know how fast is it moving in the wider section. Well, this is easy because we know that the same rate has to be true. The volumetric flow rate is the same in both parts of the pipe. That A1 times V1 must be equal to A2 times V2. So all we have to do is plug in our information. So we have 0.08 times the velocity at the wider section is equal to 0.05 times the velocity at the narrower section. So if you take 0.05 times 18 divided by 0.08, you should get a speed of 11.25 meters per second. So that means that it's traveling at 11.25 meters per second. And then once it gets to this narrow area, it's traveling much faster at 18. This leads us to the next main concept, which is actually using Bernoulli's principle. This was discovered or created by a Swiss mathematician and physicist named Daniel Bernoulli. And what he figured out is that you can use the conservation of energy for the flow of a fluid. And so you might look at this and not immediately see energy. But what we actually have here is pressure. And pressure, we know, is the force divided by the area. Well, I know that if I multiply force times some distance on the bottom and top, that's not actually changing my problem at all. But force times distance is work. And area times a distance, that's an area times at some depth, so that's going to be the volume. Work divided by volume is this very first piece right here. That's pressure. So this right here is the work done divided by the volume. The next piece of this is rho g y. Well, y is the position, so it's very similar to mgh. But if you take mgh, which is your gravitational energy, and you divide it by the volume, then really what you have is mass divided by volume here, which is the same as density. So this second part is really your gravitational energy divided by the volume. And if you do the exact same thing with this guy, again, density is really just mass divided by volume. So we have 1/2 mv squared, which is our kinetic energy. So we have kinetic energy divided by the volume. So this is really your conservation of energy equation because, again, density is mass over volume. Make sure that V looks like a capital V there. Okay. So really all these equations, and then it repeats on the other side for a second location. So really each one of these is saying that if you take the sum of the energy and divide it by the volume, it's the same. And what Bernoulli figured out is that for a fluid, that this is always going to be some constant value. No matter where you go, that you will always have the same amount of energy per volume. So this remains a constant. Each one of these terms have a specific name for it. So the first one is gauge pressure, which is a static type of pressure, which the pressure from the gauge is what we say here. But again, that is really work divided by the volume. The next one is hydrostatic. Again, static, so you're thinking that it's stationary, that it's based off of where it is position-wise. That this is equal to rho g h, where rho is the density, g is acceleration due to gravity, and h is the elevation, which is also called y. And that this is really your gravitational energy divided by the volume. And last one we had was dynamic. Dynamic means moving. So then this one is going to be our 1/2 density velocity squared. And just like before, this is our kinetic energy divided by the volume. And each one of these three pieces is put together to give us Bernoulli's principle. And again, when you add all that stuff together, it should remain constant. The units of energy per volume are exactly the same. All right, so using this equation for a fluid in a pipe, we have a couple of things going on here, but the first thing says if the height changes. If the height changes, so we go from a taller location to a shorter location like this, but we keep the actual length and the area of the tube exactly the same, then what happens is at those different locations, even if the height changes, our volume is constant because the area is the same. So if we say that A1 is equal to A2, well, since Q1 is equal to area times volume, and that stays the same, if the area stays the same, the volumes must stay the same, or the velocities must stay the same. So when we take our equation for Bernoulli, which says that the pressure at 1, the gauge pressure here, plus rho GH at 1, plus 1/2 rho V squared at 1, that's equal to the same exact thing at our second location. Plus 1/2 rho V2 squared. And since these velocities are the same, that this ends up being exactly the same as this one. The velocity stays the same, density stays the same, so I can actually cancel those terms out completely. And if the height goes from a higher location to a lower location, so let's say that we're at this location right here, that H2 is equal to 0, then that term goes away. So really what we're told is that the pressure at 1 plus rho GH, where H is going to be the change in your height, is equal to the pressure at our second location. Again, that is assuming that the areas are exactly the same and the height changes. Now, same principle, let's assume that the heights stay the same, but the area changes. So we're going to say H1 is equal to H2, so the heights are exactly the same, but area 1 is not the same as area 2. Well, if those guys are not the same, therefore velocities are not the same, because again, that flow rate must be exactly the same. And so if I bring it back to my equation, I have the pressure at 1 plus rho GH at 1 plus 1/2 rho V1 squared is equal to the same thing at our second location. Oops, I'm running out of room here. Let me bring all this stuff down. Okay. Plus 1/2 rho v2 squared. Okay. So if the heights are exactly the same, then that means instead of canceling out our velocities, we can actually cancel out our heights because those are the match. Now we cannot cancel out our 1/2 rho v squared because those two are different. And so we actually get the equation that looks like this. Pressure 1 plus 1/2 rho v1 squared is equal to the pressure at 2 plus 1/2 the density v2 squared. Now if it does both, then you would keep the full equation. You'd keep the entire thing. Again, next part here is just talking about ideal fluids. So we talked about this before. You cannot compress ideal fluids. They are essentially have no viscosity, which means they are easy to flow from one to the other. There's no resistance. And then the last one is that they flow freely. But another way to say that is they have a streamlined flow. Which is the opposite of a turbulent flow. So if you look at these, this is a laminar flow, which this is the one that we want. It's going to flow directly across straight lines, no turning and causing some chaos. Everything is just going straight there, flowing smoothly. Alrighty, try the next example on your own. So it says ranking these locations. We're going to rank the flow speed from least to greatest at each of these locations. And then we're going to rank the pressure from least to greatest. So think about what we know from the example above. What do we know about the areas? Because the areas are the same all the way across. So what does it tell us about the speed? And what does the height tell us about the pressure? All right, we'll talk about it in class. See you then.